Hello, we are Team Base. My name is Sasha, and here we have Christopher and Gloria, and we chose a Bayesian approach. Why is that? Next slide, please. Because we do not have, in fact, a big data problem, but we have a little data problem. We have just two simulations, and this will make for very big uncertainties. And also, it allows us to include a priori knowledge on the data and on the forcings that we have. I will elicit that on the next slide. So here you can see on the left-hand side, the plot is the globally averaged temperature, blue line, and the volcanic forcing, orange line, as a function of time. And you can clearly see the correlation of the two. You can also see that the time scale of the simulation response to the forcing is also very short. So we have short time scales and the high correlation. And the middle plot, in the green line, you can see the solar forcing as a function of time versus the temperature, blue and orange. And there it seems to be not so obvious. So we have a low correlation with solar forcing, and it's supposed to be a long time scale, some 50 years or something. And on the right-hand side, you can see the spatial data. And we think that volcanic forcing should be a regional effect, and solar forcing should be a global effect. That leads us to the next slide. Our approach is to model the data as a Gaussian random field or a Gaussian process, as you might know it. So we treat each simulation as a Gaussian process. We find the correlation parameters, the scales, and we track those scales over time. And here you can see the result. And in these plots, the correlation parameters as a function of time, we can basically see nothing because we made a mistake in our calculations. With that, I'd like to hand over to Christopher. Thank you.
So, due to lack of time, we couldn't check yet if it was a mistake or if there's really no correlation. So we switched to something simpler in the end, just to solve a part of the problem. Actually, you can see that there is a strong correlation of the volcanic forcing, which is called ADO here, to the temperature difference to the mean in the next year. So 1 year after the volcano breaks out, you have a strong response which you can fit linearly, more or less. And with these, you can to some degree reconstruct the volcano data by knowing only the temperature data. This is, of course, a very crude and simple model, but it solves part of the whole problem. So finally, the question, has there been volcanic forcing last year, can be answered by combining a linear fit also in the end with a Gaussian process. Solar forcing is hard to impossible to detect, which we also validated by statistical methods. We can look at how length scales and noise look over time with the Gaussian process. And all methods work if we just filter tropical and polar regions. So the conclusion is Gaussian random fields are very flexible for modeling heterogeneity. We can compare models and give uncertainties by Bayesian methods, look at different length scales, but the implementation is not trivial, so one would need much more time to have a full implementation of what we proposed. Thanks and goodbye.